Good morning, dear students. After discussion of internal energy in previous chapter, the next important topic in thermodynamics is enthalpy. Enthalpy is actually an important thermodynamic property of a system which is directly related to heat content of the system. Let us discuss about this topic. Enthalpy is actually the measure of heat content of the system, and as we all know that all physical or chemical processes are accompanied by some form of energy change, and these changes you can observe while burning a substance. That lot of heat energy is evolved out. So on the basis of these kind of heat changes or energy changes in a reaction, the chemical reactions can be classified into two types. If heat is given out, those reactions are said to be exothermic, and if heat energy or any kind of energy is absorbed by a substance during reaction, that type of chemical reaction is called as endothermic reactions. And you know that in our daily life so many examples are there for these kind of reactions, like combustion of fuels. Any type of burning releases lot of energy, and this is an example of exothermic process that we can observe in our daily life as well. And even inside our body, the respiration which is taking place due to oxidation of glucose in our cells, it releases lot of energy in the form of ATPs. So this is also kind of exothermic process. Similarly, very daily life phenomena like photosynthesis taking place in plants is an endothermic process because solar energy is absorbed in this process. Similarly, thermal decomposition of any chemical is also a kind of example of endothermic process in which heat energy is absorbed. So energy changes can take place in different ways, either in the form of heat energy or in the form of light energy or in the form of some other form of energy. So enthalpy is actually a measure of heat content of the substance at constant pressure, because generally all the natural processes are taking place at constant pressure, generally at atmospheric pressure. So the heat changes taking place in that condition in a system is actually related to the enthalpy of the system, and it is the amount of energy in a system that can be converted into heat. It is represented by the symbol H. Actually, we cannot measure the actual enthalpy of a substance, rather we measure enthalpy changes, and enthalpy change for a reaction is denominated by a symbol delta H, and delta H is actually the difference of the enthalpy of products and enthalpy of reactants. So first of all, we'll mathematically describe what enthalpy is. As we have done in internal energy topic, that the heat supplied to a system at constant volume is equal to change in internal energy of the system. But actually the processes, thermodynamic processes which are taking place in our surroundings are at constant atmospheric pressure, in which the volume doesn't remain constant. So in that case, if we talk about constant pressure, then the equation for delta U will be equal to, delta U is equal to QP minus P delta V. Here QP is the heat supplied or heat absorbed or released by the system at constant pressure. And this equation we have also derived in first law of thermodynamics. Next, we can also write this equation as QP is equal to delta U plus P delta V. Now, changes in internal energy and change in volume for a process, we can write the equation as U2 for the final state and U1 for initial state. Similarly, volume V2 is for final state and V1 is for initial state. So in terms of initial and final state, we can write delta U and delta V as we have written in this equation. And now we can also write it as QP is equal to U2 plus PV2 minus U1 plus PV1. Here this term U plus PV is actually a new state function which is called as enthalpy, and it is represented by H. So this is another new useful state function in thermodynamics which is called enthalpy content of the system, which is equal to internal energy plus product of pressure volume. Now in place of U2 plus PV2 and U1 plus PV1, we can write H2 and H1. So we will get this equation QP is equal to H2 minus H1, or it is also known as delta H. So we can say that heat supplied or heat changes during constant pressure in a system is directly equal to the change in enthalpy of a system. So in this way we can measure the change in enthalpy by just knowing the amount of heat supplied to the system or released by the system at constant pressure. So we can define enthalpy change as the amount of heat absorbed or released by a system at constant pressure. And if we put the value of QP in the first equation, we'll get delta H is equal to delta U plus P delta V. This is our important equation which we can use for calculations of enthalpy change from internal energy change for a particular process. For systems involving solids and liquids, there is not a significant change in volume during a process. So delta H and delta U values are quite similar to each other. But for a system involving gases, there is a significant change in volume. And for gaseous systems involving gaseous reactants and products, we can calculate these changes as we know that for an ideal gas, PV is equal to nRT. And suppose in a chemical reaction, gaseous reactants are changing into gaseous products, then we can write this for reactants. Let us say in N1 moles of reactants are participating in the reaction of a gaseous substance. So for those gaseous reactants, we can write PV1 is equal to N1 RT, and suppose N2 moles of products are formed in the reaction, so we can also write PV2 is equal to N2 RT. Now we can put the value of PV2 and PV1 in the equation written above, and hence we can get this equation: delta H is equal to delta U plus N2 RT minus N1 RT. And this we can also write delta H is equal to delta U plus delta Ng RT, as R and T are constant. Only the difference in number of moles is there, and this difference can be written as delta Ng. This is actually number of moles of products in gaseous state minus number of moles of reactants in gaseous state. So this is how we can calculate enthalpy changes for reactions involving gaseous substances. Let us see with the help of one example. If water vapor is assumed to be a perfect gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. Calculate the internal energy when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. So in this question we need to find delta H for vaporization of 1 mole of water. So let us see, as it is written in the question, the change taking place here is 1 mole of water is converting into 1 mole of water vapor. So we need to use the equation delta H is equal to delta U plus delta Ng. Internal energy change is given here as 41 kilojoule per mole, and delta Ng we can calculate by just looking at the number of moles of products minus reactants, but both of these are in gaseous state. Here you can see that reactants are in liquid state, so number of gaseous reactants will be 0 here. So delta Ng will be equal to Np minus Nr, that is 1 minus 0 is equal to 1. As no gaseous reactant is present here, only the product side or right hand side we have gaseous mole, that is 1 mole. And now putting all these values, we will be having delta U is equal to 41 minus 1, that is the delta Ng value, multiplied by value of R 8.314 and 373 Kelvin temperature. We will get the answer 37.904 kilojoule per mole. So this is how we can calculate enthalpy changes from internal energy changes for a system involving gaseous substances. Next, enthalpy changes in thermodynamics. Actually, how enthalpy changes while a reaction is carried out. So during a reaction, as we know that enthalpy change can be calculated by heat content or enthalpy of products minus enthalpy of reactants. So if a reaction is carried out in such a way that heat content of products is lesser than the heat content of reactants, that means enthalpy of reactants is higher than the enthalpy of products, as you can see in the graph, then that extra amount of heat will be given out by the substances during that change, because products have lesser amount of enthalpy as compared to the reactants. So that equivalent heat is given out by the system to the surroundings, and these kind of reactions are said to be exothermic reactions. And in these reactions, delta H is actually negative. Sign convention for exothermic reactions are negative because the heat is given out to the system, given or released by the system. So it will result in decrease of enthalpy content of the system. Hence delta H is given negative sign. Next, here we can see enthalpy change during an endothermic process. Suppose reactants have lower enthalpy content but the products have higher enthalpy content. So such type of reactions take place by absorption of energy from the surroundings, and during this absorption the actually enthalpy content of the products is increased. So here, as the enthalpy is increased, so sign convention, according to the sign convention, delta H is positive for endothermic processes. So always remember this thing: for exothermic reaction, enthalpy content or the sign of enthalpy change is always negative because heat is lost by the system. Whereas for endothermic processes, enthalpy change is given positive sign as heat is absorbed by the system. Next, now standard enthalpy changes taking place in a reaction. Actually, reactions can take place at various conditions of temperature and pressure, and these enthalpy values vary according to the conditions. Moreover, if a substance is present in different physical states, then also amount of energy vary for a particular reaction. So standard values are to be obtained for a particular process, and these values are taken as reference values, and for these values standard conditions are taken as pressure 1 bar and temperature generally 298 Kelvin, that is room temperature. And also it is important to mention the correct or the most stable standard state of a substance at which it is existing in normal lab conditions. And if a solution is used, so the concentration which is taken as standard is 1 mole, 1 molar you can say, and standard conditions are used as the symbol, we can say it is delta H naught is written to express standard enthalpy changes for a particular process. So next is, now we'll discuss various types of enthalpy changes associated with various processes. For a simple chemical reaction in which the substances react completely to form products, so the change in heat energy, either the heat released or absorbed, is said to be enthalpy change of reaction, and the symbol used is delta RH. For example, you can see here, when carbon combines with oxygen to form carbon dioxide, this heat changes are, or this heat evolved during this process is minus 393.52, where a negative sign indicates the process is exothermic. So for all these reactions, the heat contents are actually the heat changes taking place during the system. And for writing equation For considering enthalpy changes of a reaction, the equations must be balanced in terms of all different atoms. Next is enthalpy change of formation. Formation means when 1 mole of a substance is formed from its elements in their most standard states. So the amount of heat released or absorbed is actually called as enthalpy change of formation. Actually, enthalpy generally during formation, enthalpy changes are negative. Means most of the substances, when they are formed by their elements, generally enthalpy is decreased, means heat is evolved out. And remember this thing, that whenever we need to write equation for formation of any substance, the substance which is to be formed as a product must be taken for 1 mole only, and we need to balance the reactants accordingly. And always remember, whenever carbon is involved in formation of any substance, the most stable state of carbon in thermodynamics is considered as graphite. So always graphite is used to write enthalpy changes, or to calculate enthalpy changes of formation of any substance containing carbon in it. And one more important thing, elements in their most standard states always have zero enthalpy of formation. And next, if these substances are taken in their standard states at standard temperature and pressure, so the term enthalpy change is known as standard enthalpy change of formation, which is expressed by the symbol delta F H naught. Now, enthalpy change of combustion. Combustion is a reaction in which a substance burns completely in oxygen to form carbon dioxide and or water vapors, etc. And generally combustion reactions are always exothermic in nature, means heat is evolved out. And here important is that the substance which we are burning is taken as 1 mole. Remember the difference. If you are calculating energy changes for formation, then always the product is taken as 1 mole, which is to be formed. But when we are writing equations for enthalpy changes of combustion, the substance which we are burning is taken as 1 mole. As you can see in all these examples, the substance which is burnt here, like graphite, hydrogen or ethanol, they are taken in 1 mole, and we can balance the other species accordingly. Similarly, if the calculation for enthalpy changes are done at standard temperature and pressure according to the thermodynamics, then it is said to be standard enthalpy changes. Next is enthalpy change of phase transformation. Phase transformation means when a substance changes its physical state, then the heat associated with that particular transformation is said to be enthalpy change of phase transformation. But here again, the substance is to be taken in 1 mole quantity. So first of all, enthalpy of fusion. Fusion means when 1 mole of a solid substance changes into liquid state at melting point, the changes associated with the process are called standard enthalpy of fusion. For example, here you can see 1 mole water when changes into 1 mole of ice when changes into 1 mole of water, the heat absorbed by ice is 6 kilojoule per mole. It's known as enthalpy of fusion of ice. Similarly, enthalpy of vaporization, when 1 mole of liquid substance changes into gaseous state at boiling point and at 1 atmospheric pressure, then at that time it is said to be enthalpy of vaporization. For example, when 1 mole of water changes into 1 mole of water vapor, the enthalpy change or the heat absorbed here is 40.79 kilojoule per mole. Similarly, enthalpy of sublimation, if a substance changes from solid state into directly gaseous state, then the process is known as sublimation. And if it is taking place at constant temperature and atmospheric pressure, then it is said to be enthalpy of sublimation. The heat changes associated in this process. So, carbon dioxide in dry ice form. sublimes into gaseous form, and for 1 mole of this conversion the heat changes are 25.2 kilojoule per mole. So in this way we can find variety of enthalpy changes associated with various physical as well as chemical changes. Next is bond enthalpy. Bond enthalpy is actually related to chemical bond formation. Whenever a chemical bond is formed, some amount of energy is released. So that equal amount of energy is required to break that chemical bond. So it can be defined as amount of heat energy required to break 1 mole of a chemical bond to obtain gaseous atoms. Always remember here that substance is to be broken down to obtain gaseous atoms only. Then the energy changes will be associated with bond enthalpy. If the substance is a diatomic molecule, then generally bond enthalpy is equal to twice of enthalpy of atomization. Enthalpy of atomization is actually the amount of heat energy required to break a molecule into its constituent atoms in gaseous state. So this is what equivalent to the bond enthalpy if a substance is diatomic gas. Okay, but if for polyatomic molecules, the bond enthalpy is actually taken as the mean value of all similar types of bonds present in that particular molecule. And smaller the bond enthalpy, weaker would be the bond, easier it will be to break that bond. Next is very important law, Hess law. Actually, this law is related to the fundamental basic principle that enthalpy is a state function. That means enthalpy change in a process is independent of the path taken. So this law states that if a thermodynamic process can be carried out in a number of steps, then the total amount of enthalpy change of the direct process is equal to the sum of all enthalpy changes taking place in those different steps. For example, here we can see if A is converted into B in direct process and enthalpy changes is equal to delta H, then if the same process is carried out in small steps or different steps from A to X and then X to Y and then finally Y to B. Here X and Y can be considered as intermediate products. So finally to obtain B, if we are having 3 steps here, so all these enthalpy changes taking place in these 3 steps, the sum of these will be equal to delta H. So this is what Hess law, which is actually based on the principle of you can say state function. So Hess law can be used to calculate variety of enthalpy changes taking place in different processes. For example, enthalpy changes which cannot be measured directly. For example, enthalpy change of formation and enthalpy change of any reaction. If we cannot measure them directly, so we can calculate them by using variety of different enthalpies like enthalpy change of reaction from bond enthalpy, enthalpy change of reaction from combustion enthalpy, enthalpy change of formation from formation enthalpies or combustion enthalpies, etc. Let us see how we can calculate them. Firstly, enthalpy of reaction from bond enthalpies. Imagine during a reaction, all the bonds of reacting species are broken and individual atoms join up again but in the form of the products. So the overall energy change will depend on the difference between the energy required to break the bonds and that released as bonds are made. मतलब जितनी एनर्जी आपको रिक्वायर्ड है रिएक्टेंट्स के बॉन्ड्स को ब्रेक करने के लिए और जितनी एनर्जी रिलीज हो रही है नए बॉन्ड्स बनने के टाइम पे अगर हम उनका डिफरेंस निकाल लें तो ऑब्वियसली विल बी गेटिंग द चेंज इन यू कैन से enthalpy taking place in that particular chemical reaction, because chemical reaction is you can say an rearrangement of atoms by breaking of older bonds and formation of new bonds. So hence we can say delta H for a reaction can be calculated by sum of bond enthalpies of all the reactants and subtracting sum of bond enthalpies of all the products. Also, we can calculate enthalpy of reaction from enthalpies of formation. Means if we are given formation enthalpies of reactants and products, then by applying this simple formula that reaction enthalpy can be calculated by subtracting total enthalpies of formation of reactants from enthalpies of formation of products. So this is how Hess law has successfully given the formulae for calculation of enthalpy changes associated with various processes in which we can directly not calculate the enthalpy changes. Here we can have one example. Calculate the standard enthalpy change for the following reaction in which standard enthalpies of formation of water, nitrogen dioxide and nitric acid are given as, and the value of oxygen is 0 as it is an element, and the formation of nitric acid in liquid form is taking place from these substances. So we can directly apply the formula delta H for this reaction is equal to delta H of formation of products, that is nitric acid, minus sum of all the enthalpies of formation of reactants. And now we can have the values 4 multiply, as the number of moles of nitric acid are 4, so we need to multiply the amount of enthalpy change with 4 because the formation enthalpy is given for 1 mole only. And similarly for reactants, 2 moles of water, 4 moles of nitrogen dioxide, 1 mole of oxygen. But always remember, elements in their pure form, standard form, most standard form, have 0 enthalpy of formation. So on putting the values, we can get answer minus 252 kilojoule. Next, one more example we can have following Hess law. Enthalpy of formation of methane, how we can calculate it. In this question, we need to calculate enthalpy of methane gas formation at 298 Kelvin if standard enthalpies of formation of CO2 and water are given as, and combustion enthalpy of methane is minus 890.30 kilojoule per mole. Here we need to write aim for this reaction because we need to form methane. So always whenever we need to write formation reaction, form 1 mole of methane by the constituent elements in their most standard state, that is carbon in graphite plus hydrogen in gaseous state. As in methane, 4 hydrogen atoms are there, so write 2H2 in this equation to balance it. Next, we will write equations for enthalpies of formation of CO2 and H2O as the values are given. So equation will be written to balance 1 mole of CO2 and H2O as these are enthalpies of formation given to you. And similarly, combustion enthalpy of methane, the reaction will be of combustion of methane but using 1 mole of methane which is to be burnt. Now we have these 3 equations, we will give number to these equations as 1, 2, 3. Now applying Hess law, what we need to do is we can add or subtract these thermochemical equations as we are doing simply in mathematics. So we'll to get our aim equation, we'll add equation 1 and 2, but before adding them we need to multiply second equation by 2 because in our aim we have 2 hydrogen molecules but in second equation we have just 1 hydrogen molecule. So what we will get, multiply equation 2 by 2 and add equation 1 and 2 and then subtract equation number 3 from that. So here we have this after adding 1 and 2 and subtracting 3, we'll be getting, obviously when we are multiplying second equation by 2, we need to multiply the value of enthalpy change also for that. So after solving this, we'll get the final equation which was our aim. So basically we need to obtain aim by using these thermochemical equations by adding or subtracting in any way that we get the desired equation, and accordingly we need to solve the values of enthalpy changes for individual steps. As we are doing with equations, same is to be done with the values. So here answer for enthalpy of formation of methane is minus 74.8 kilojoule per mole. Hope the things are clear to you all. Thanks and have a nice day.